Hi everyone, welcome back to the first module, Windows Internals Overview. In the Windows Internals Overview, we will take a look at the process internals, the PE formats, the Windows architecture, and the execution flow from user mode to kernel mode. Let's start by user mode presentation of a process and its properties, starting by some general informations about the process. So a process acts as a container that separates application from each other. This ensures that one application cannot interfere with the memory or resources of another, enhancing system stability and security. A process manages critical system resources, including threads that are units of execution that run the actual code, handles that are references to system objects like files, directories, events, or registry keys. It manages also the token, which is security identity that defines user privileges and permissions. It manages also memory that allocates and manages virtual address space. A process itself doesn't run any code. Instead, threads within the process execute the code. A process can have one or more threads running concurrently, sharing the same resources but executing independently. Every process is uniquely identified by a process ID, a PID, and not by its executable file, because we can see multiple processes that are using the same file image, like launching 5 CMD processes. Each process has its own address space, its own threads, its own handle table, its own token, and its own PID. A process can be parentless, meaning created by the system, or under a parent process, meaning launched by another process. If the parent process dies, the child process remains unaffected and continues to run. Every process has an integrity level, either low, medium, high, or system. This defines the level of access and actions the process is permitted to perform on the system. For example, a low integrity process is heavily restricted, limiting its ability to modify files or settings. Some processes are marked as protected processes or protected process light. These are designed to prevent tampering, termination, or code injection by unauthorized processes. They are typically used for critical system components like antiviruses, system processes, to safeguard them against malware attacks. Now let's see those properties in action using Process Hacker. So let's open Explorer.exe process and any other process. And we can see that the process is just a container that contains threads, token, memory, handles, and each process acts as a container that separates applications. Each one has its own token, threads, memory, and handles. And the process itself doesn't run any code, so the threads do so. And we can see here is the thread called stack that is running some functions, and this is a list of function calls that represent the execution path a thread has taken to reach its current point, starting from user mode using intdll.dll rtl user thread starts at this offset, and finishing at the kernel at this kernel function key check for kernel APC delivery at this offset. So a process is uniquely identified by its PID. To check that, let's run a couple of CMD processes, a tree one with medium integrity, and search for CMD. I already run other CMD instance with a high integrity, but the ones that we just run are those, the medium integrity instance of CMD, and we can see that they have the same properties. The only one thing that identify each one is the PID, and each PID of each instance is different from the other. And as we are running this CMD instance from the Explorer, and we can see here that the parent of those CMDs are explorer.exe, and if I run PowerShell within this CMD and search for PowerShell, we can see that its parent is actually, in fact, the CMD with PID 1872. And to check that, let's put that, and we can see that its PID indeed 1872. And if we kill this CMD with PID 1872, the child remains unaffected. 1872 and terminated. It's terminated, but the PowerShell process remains unaffected, and it tells us that its parent process is non-existent, but it was having this PID 1872, and this is the PowerShell. It's still working. The other property is we saw that each process has an integrity level that is low, medium, high, and system is the most powerful integrity. And we talked about protected processes. We can see that by launching Process Explorer sysinternal, and we can see different processes with different protection level, like MS MPENG that is protected with anti-malware light, and LSAS is normally protected with LSA light protection, but in this machine the LSA protection is removed. We can see that in action using another machine, and if we monitor the protection level of LSAS here, we can see it's protected with LSA light protection. Now let's skip. Now the next thing is the integrity level, and we have 4 integrity levels: the low integrity, the medium integrity, the high integrity, and the system integrity. The low integrity is the least trusted level used for applications handling untrusted content like web browsers. It can only interact with other low integrity processes, ensuring isolation from more sensitive applications. It has very limited write access, restricted to specific locations like user profile app data local low, and minimal access to HQ current user registry key. This prevents any harmful changes to critical system settings or user data. The next integrity level is the medium integrity. It is the default level for most user applications, including File Explorer and Microsoft Office. It can interact with both medium and low integrity processes. It can write to user-owned directories like documents, downloads, desktop, and access the HQ current user. The next integrity level is the high integrity. It's for applications with administrative privileges, such as system management tools. It can interact with high, medium, and low integrity processes, giving it broad control over the system. It can write to protected directories like C windows and program files and has full access to the registry. However, it requires user approval via UAC to launch, preventing unauthorized elevation of privileges. Now let's talk about the system integrity, which is the highest level, reserved for core operating system components. It can interact with all integrity levels and has full access to the entire file system and registry. This level is heavily protected to prevent tampering, ensuring the stability and security of the operating system. Now let's take a look at process protection levels. Process protection levels define the security status of a process based on two factors: the signer and the protection. The signer identifies who signed the process, either Windows, anti-malware, and the protection type determines the strength of the protection, either protected or have a light protection, which is protected light. Now let's see some very familiar protection level. And the first is the PS protected system, which is signer is the Win system signed by the Windows system itself, and its protection type is protected. The Win system value is 2, and the protected value is the Win system value is 7, and the protected value is 2, which forms the protection level value of 72 in hexadecimal. And protection type is protected, which is the highest level of protection. The purpose of this protection level used for hypervisor related processes like the secure kernel, providing the most robust security to prevent tampering or termination. And the next protection level is PS protection LSA Lite, which is used as it shields in the local security authority from attacks, particularly to prevent credential theft tools like Mimikatz, enhancing system security. And the signer of this protection level is LSA with value as 4, signed by the local security authority, and the protection type is protection light. Its value is 1. It's a light protection level, which using the combination of two values will form a protection level value of 41 in hexadecimal. The next protection level that we will see is PS protected anti-malware light. Its value is 31 in hexadecimal, and the 3 represents the signer, which is the anti-malware signed by the anti-malware software vendors, and the 1 is the protection type, which is protected light. And the purpose of this protection level is to secure, it will secure antivirus and anti-malware software from tampering or disabling by malicious processes, ensuring continuous system protection. Now let's take a look at the mitigation levels. And process mitigation policies are security features in Windows designed to reduce the attack surface and protect against common exploitation techniques. These policies provide layers of defense to make it more difficult for attackers to execute malicious code or manipulate memory. Let's go through the key mitigation policies. We have the data execution prevention, or the DEP. Is designed to prevent code execution from non-executable memory regions, such as the stack or the heap. This means that even if an attacker managed to inject malicious code into these areas, the code cannot be executed, blocking traditional buffer overflow attacks. And next we have the ASLR, address space layout randomization. Randomize the memory addresses where executable DLLs and heaps are loaded. This randomization makes it extremely difficult for attackers to predict memory locations, which is essential for attacks like return-oriented programming, ROP, and code reuse. By shuffling the memory layout each time a process is started, ASLR ensures that even if an attacker discovers a vulnerability, they cannot reliably exploit it because the target address keep changing. This significantly increases the complexity of the exploitation. Next is the Control Flow Guard, the CFG. Is a security feature that prevents memory corruption exploits by ensuring that code execution only follows legitimate control flow paths. Next mitigation policy is signature restricted, Microsoft only. Restricts code execution to Microsoft signed binaries only. This means that only executable or DLL that is not signed by Microsoft will not run, blocking unauthorized or malicious code from executing. And the next mitigation policy is images restricted. Blocks the loading of executables and DLLs from network shares such as SMP and WebDAV. This prevents attackers from executing code remotely by leveraging network resources.